Welcome back to another video on the channel. In today's video, we're going to be taking a look at the 2020 short response question 13 from the Specialist External Exam paper 1. Now, you would have noticed with all the videos, I've started splitting them up into their own video for each question. That way, I can go into a bit more depth on each question, and if you only struggle with a certain question, you can go watch that exact video. If you need any help at all, there is a forum in the description below where you can submit your own questions, etc. And I'll try my best to answer them and I'll send them back to you, or I'll make a video on it. The full playlist for the full external exam is in the description below as well. There is a specialist external exam bundle pack in the description below, and there's a discount code that will take 50% off, and it'll only work for the first 10 users. So if you use it at checkout, you should be able to get 50% off it. Okay. But otherwise, let's just get straight into question 13. Now, question 13. A lot of people don't even know how to start this one, okay? So, the expected value of an exponential function, random variable x, with the parameter lambda is greater than 0 can be determined using this rule here. Now, everyone looks at that and they think, oh dear, how do we even do this? Well, for starters, they say use integration by parts, okay? So, if you know how to use integration by parts, you should be able to start it. Now, a big idea we want to incorporate in math is if you don't know what to do, just think about what you can do and just do it, okay? Because more or less, you'll probably go down some sort of rabbit hole, whether it's correct or incorrect, but that's better than nothing if you have no idea what you're doing, okay? So here, use integration by parts to determine the expected value, express it in the simplest format. So, here, let's not worry about the bounds for now. Let's just look at this integral here, x lambda e negative lambda x, okay? Now, let's also look at integration by parts. Integration by parts is given by roughly this. It's like the reverse product rule, okay? Now, ideally, what we want to pick is a function that is going to differentiate quite easily and a function that's going to integrate quite easily. So, what you would pick for your u in integration by parts is a function that disintegrates. Okay, if you differentiate it a couple times, you'll turn to a constant. So, in this case here, the x is what I'm going to pick for my u, because if I differentiate x, it will turn into 1. Whereas if I differentiate the exponential, it still remains. So I'm going to integrate this guy here instead. Once you make that choice, it's all pretty easy from there. Then again, if you make the incorrect choice, you will get a worse integral than what you've started with. So then you could backtrack. Okay. So let's say you've made this choice here. What we've got to do is, 1, differentiate this. So if you differentiate this, u dash turns into 1. When you integrate this, the integral of e remains the same. However, you have to divide by the differential of this. Now, the differential of that is negative lambda, because lambda is a constant. So v will turn into lambda e negative lambda x all over negative lambda. The lambdas cancel out, so you get v equals negative e negative lambda x. And that's it. Okay? Once you've done that, it should be pretty easy then to start subbing it in. Now, we will take a look at the bounds, because the bounds will have some significance in this question here. So, let's write it out. So, the integral from 0 to infinity of x lambda e negative lambda x turns into u times v. So, in this case here, that's going to be x times by this term here. So, times by negative e negative lambda x, and that's going to be between 0 and infinity, minus the integral 0 to infinity of u dash, which is 1, times by v, which is negative e negative lambda x dx. Now, if it helps, you could put a limit in there instead of infinity. However, the infinity should be fine here. I don't think you're going to lose marks for keeping the infinity in. Okay? Alright. Now, let's start evaluating the first bit. So here I'm just going to move that away, because you don't need the by parts formula anymore. Okay? So here, let's start looking at this guy here. So if I were to start evaluating this guy here, what we've got to do is just think, alright, what bound would go in first? Well, the bound that would go in first would be the upper bound. Agreed? So here, what we're going to do now, instead of chucking in infinity, we'll just rewrite this as a limit. So we can just replace that with like an a, and we'll just say the limit as a goes to infinity, which is basically the same thing. So if I chuck in the a, I'll get this. Now, before we do anything, let's rewrite how this actually looks as well. Because that's a negative exponent, I can write that under a fraction. So I can rewrite this entire thing as x over negative e lambda x. Okay, that's going to be a lot easier to work with when we look at this brand new, well, not a new idea, this idea here. Let's chuck in a now. Okay, so upper bound goes in first, so you have a over negative e lambda a minus 0 over negative e lambda times 0. This term fully disappears, so we don't have to worry about that. Now, let's look at this guy here, because remember, the limit is still present here, because a represents infinity. So, as a goes to infinity, this term here is going to get significantly bigger than this, okay? Because an exponential term is more powerful than a linear term. So, as a goes to infinity, the denominator is going to go to infinity. Now 1 over infinity is going to be 0. So as a goes to infinity, a over negative e lambda a will go to 0. So this term is 0 basically at infinity. So we can get rid of that. So let's get rid of that. Now that's quite hard to understand. So if you have any questions about that there, leave something in the comments there. Okay. So we are left with this at the moment, which is a lot easier of an integral to work with. Now, I would take the negative outside the front, so you have positive. Now, I'm going to replace the infinity with a limit again. So the limit as a goes to infinity, the integral 0 to a e negative lambda x dx. Now, that's a lot easier to integrate now. So, let's integrate that. So, if you integrate that, it's going to be e negative lambda x divided by the differential of the inside function, which is negative lambda, between 0 and a as the limit as a goes to infinity. Okay. Now we're going to chuck in the upper bound and the lower bound. So if you chuck in the upper bound, you'll be left with e negative lambda a over negative lambda. Subtract e negative lambda 0 over negative lambda. Now remember, the limit is still present. Okay, so here we've got to take a look at this. Now I would rewrite both of these expressions. I would move both exponential terms below hand, which I probably should have done in the first place, but that's okay. So here I'll just make this a bit smaller. So here I'll have 1 over negative lambda e lambda a. Now here I'm going to replace that with a positive because there's two negatives. 1 over lambda e to the power of 0. Now this is still the limit as a goes to infinity. Now remember, as a goes to infinity, 1 over negative lambda e lambda a will turn to 0. So this disappears as the limit occurs. Means we're left with just this bit here. Now e to the power of 0 is 1. So it's just going to be 1 over lambda is all we've got left. So your expected value for x of this guy here is just 1 over lambda. Now in Specialist, you should have actually seen this guy before. You've never had to do this activity probably. However, you've definitely seen this formula before if it's an exponential curve that looks like this. You should know the expected value is 1 over the lambda value, which is this term here. If you don't, you need to review that a bit more. It's a special type of probability density function. Anyways, a lot of working for 4 marks. Is it a hard question? Yeah, absolutely. Okay, because it'll show that question. Will you get something like this year? Who knows, maybe. Okay. If you need any extra help, you might need to get the Specialist External Exam Bundle Pack. The link is in the description below. Use the code at checkout to get 50% off. The full exam is also on YouTube. Link is in the description below, so go check that out. If you have any questions, leave something in the comments as well. But otherwise, I'll see you in the next video.